before the closing, or is it tea and coffee and all kinds of stuff. There's still loads to do. Welcome to this session. We've got Luke Peter, who is going to be, I'll leave it to him to explain the organisation he's working for. I'm sure you've heard of it. It's just been recently bought out, and he's going to do a very, very interesting presentation right now. Luke, over to you.
Good afternoon, everybody. Can you hear me? Fantastic. So what we're looking at today is an implementation of wireless condition monitoring and how we use that technology to reduce downtime by quite a dramatic amount on our critical assets inside of a beverage can manufacturing company. They're not currently who I'm with at the moment, but I'll get through a little bit of my background as we go through this. So the system was designed and sold by Waits and supported by GVS, who supplied the products in Australia and assisted with installation. So about me, my background is, by training, I'm a mechanical engineer. Outside of university, I started working at Sappi in Southern Africa, which I suppose is similar to Visi over here in terms of what they do. Heavy manufacturing, pulp and paper industry. I was the mechanical area engineer in that section, responsible for asset maintenance and reliability for a pulp drying continua. And I was exposed to the benefit of being supported by a very, very well-staffed condition monitoring team in that environment. There were 5 dedicated analysts that were on our payroll, as well as 4 data collectors, a reliability engineer, and a number of technicians, which meant that I could get data, vibration data whenever I needed it. I could get it at short notice, and I could get it as often as I wanted. And we could do that because the price of labor in South Africa was not extremely high. I finished up with Sappi as their regional reliability manager, covering the implementation of an RCM process known as MSG3 on the assets on our various mills in the state that I was deployed. So that's the environment that I started in. And then moving to Australia, I found that the environment was a little bit different. I was in a large 24/7 beverage can producing plant, and despite having a similar amount of turnover and profit, they were definitely not supported by the same amount of people, if that makes sense. The cost of labor in Australia is prohibitively large, so the company couldn't really justify the headcount to have a dedicated team of vibration analysts on site. So that came as something of a shock for me. So that's where the Waits solution comes in, and we'll talk a little bit more about that later. Following my time at the beverage can manufacturer, I have moved into regional maintenance management for CSR Exteriors in Queensland, and just more recently I've taken a trip onto the dark side of things and gone into manufacturing management for the same plant. So at this stage now I turn dirt into bricks and hopefully money. So the environment that all of the organizations that I've operated in is 24/7. It means that the cost of downtime is prohibitively large, and at some point throughout all of the days of the year, work is being undertaken. So there's not really opportunity for us to turn the plant off and get maintenance done because we're expected to make stuff all the time. So in an environment like that, production downtime becomes incredibly costly. So it's not the cost of the assets themselves that have failed, but the cost of lost production opportunity that generates the real buyback when we're trying to evangelize a reliability program. So some of those problems can be summarized as you see on the screen there. First and foremost is safety. So whenever we have to get involved in breakdown maintenance, invariably we're doing a job that we haven't done routinely. It's not day-to-day work. It's often moving incredibly large pieces of equipment from place to place, introducing hazards in the workplace that we would otherwise not be exposed to. The obvious and easily quantifiable one is production loss. When our assets aren't doing what they're supposed to be doing, we can't make product, and we can never get that time back, especially if we're expected to be running 24/7 throughout the whole year. There's no clawing back that time. It's lost. It's gone. The production opportunity no longer exists. Then obviously the cost of secondary failure. I know that in my industries that I've worked in, and I'm sure in many of yours, you have niche equipment made by 1 or 2 OEMs in the world, meaning that the spares are expensive and they take a long time to get to you if you need them in a hurry. Like You can't just hop onto the phone and have something delivered that afternoon. It's 6 to 12 weeks away, and it's prohibitively expensive. So that's another additional cost on top of that. And then the possibility that you hurt the environment because of a piece of your equipment failing. It hasn't really been an issue too much where I've been, but I know if you're working in oil and gas, when your equipment reliability isn't on point and you have unplanned breakdowns, you cause environmental damage that also has a significant reputational damage for the company. So how do we go about dealing with this? I think in man's attempt to solve this problem, entire professions, most of ours, and governing bodies have arisen. So we've always now, since the Industrial Revolution, been trying to make more things with less cost, ultimately to improve the profitability of the company that we're working for. And in order to do that, a number of strategies have been developed, and I'm sure that none of this is new to most of you because it's reliability engineering 101, but the simplest of which is we run something until it breaks, and then we change it and run that thing until it breaks. And that's called run to failure, and in many cases that's actually an acceptable strategy. If the costs of that downtime, the cost of that failure are not significant, then it doesn't make sense to spend time maintaining that asset. Then you've got preventative maintenance, which is pretty much how everybody's automobile is run, where you'll drive a certain amount of kilometers and do a certain amount of stuff to that system in order to repair it. Condition-based maintenance then is based on inspection, so you might be doing it at a certain frequency, but you're going to look at a piece of kit, you're determining if anything is wrong with it, and then making a decision on how you're going to maintain it. And then in the space where we like to live primarily, which is in predictive maintenance. So inside of predictive maintenance, we're utilizing sensors that go far beyond the realm of human sensitivity to anticipate when things are going to go wrong with enough time for us to fix that. So describing that particular process, the DIPF curve is something that a lot of you will be familiar with, but essentially the part that I care about here is the space between the P and the F. So that's when we have a fault that has been initiated, and as we progress towards the right of the graph, it becomes easier and easier to determine what that fault is, but the damage that it has caused becomes greater and greater as we go along. So the idea is to use the sensors that we have in the toolbox to determine right here early on when we have a potential failure, and then apply the correct maintenance techniques based on that condition to extend the time from P to F so that we have time to do it in a planned outage, if it is at all possible. Obviously, in a perfect world, this is the space that we would live in, the D and the I. So we would design parts that could operate reliability, and we would introduce no defects during our maintenance. That's the whole topic of precision maintenance. I'm sure that many people have spoken about that already today, so I'm not going to delve too far into that. But the idea is that we introduce no defects. The reality is we very frequently do introduce defects when we're maintaining things. So by using condition-based maintenance, we don't open up bearings to look at them because we don't need to. So we don't allow for the possibility for dirt ingress and anything else that could harm the equipment beyond what the condition it already is in. So what tools do we have to make this happen? Inside of the predictive maintenance space, we use ultrasonic analysis, we do vibration analysis, we'll do spectrography and oil analysis. There are many, many tools that we can use that are more sensitive than the good old look, listen, and feel that we ask our artisans to do on a daily basis. We'll be looking specifically at vibration analysis for this implementation, with, I suppose, an element of thermography in it as well. So the challenges that I was facing, that the company was facing there, I've pretty much detailed. So large cost of downtime, incredibly large cost of labor, and operating under the assumption, therefore, that the cost of downtime far outweighs the cost of monitoring. So this makes sense if your business is a 24/7 institution where you're making stuff constantly and you need to claw back whatever time you can from production loss. I know that increasing headcount is hard. It's hard in the institution that I'm at now, and it's been hard everywhere. So if I wanted to justify to have a permanent vibration analyst on the payroll, that would be far more difficult than it would be to justify spending money on a technology, for example. And One of the other challenges is the logistics of taking data when you're doing vibration analysis. So running equipment is often behind guards. We need it to be running when we're taking data, and sometimes that's 30 meters up in the air without any clear access. That's where the wireless portion of this comes in handy, because we don't have to run power to that space, we don't have to put humans in that environment, and we don't have to disassemble guards in order to access things. So in the case of the company that I was at, the beverage can manufacturer, they had transitioned from sort of 5 out of 7 days manufacture, very rapidly responding to market demand, to 7 days out of 7, 365 days of the year. So they had to go from what I would consider a relatively unfit maintenance organization to a very, very fit and lean maintenance organization, because productivity was that much more important. They couldn't turn the plant off and fix things and make up their production with an additional shift on the weekend, because all of that production time was spoken for. So the progress for that plant was going from no VA originally to route-based VA, to route-based VA with tethered sensors where they didn't have access to the sensors, and then ultimately to wireless sensors that were always online, giving us information as we needed to. Now, the weights solution, what they offer, has essentially 2 tiers. I'm sure you can chat to the GVS team downstairs afterwards if you need more information. But primarily they offer a self-service model, which allows you to set up the sensors yourself, you set up your alarms yourself, you manage the system and you manage the alerts yourself. What that does require is that you have somebody that understands the squiggly lines in a way that lays them out straight so everybody can understand. And again, we run into the problem that not everybody that you employ is going to be a Cat 2 vibration analyst. So what do you do then? So as the amount of sensors grew, we transitioned to the full service model. So initially we started with 50 sensors, and those sensors were deployed to our most critical assets, all of which are within around, I'd say in that installation, within 100 meters of the central point that we had attached the gateway, and we managed to get everything inside that radius connected correctly. We managed the limits ourselves, and we looked at the exceptions ourselves and hoped that everybody was paying attention when they needed to be as the email alerts were coming through. But it relied at that stage on my somewhat inexpert interpretation of the vibration spectra, and also on my ability, at that point I was the reliability engineer for the area, on my ability to fit the analysis of the vibration system into my day-to-day. And I know that industries here are very, very lean in terms of their structure, so I was often doing maintenance management support, work management on the floor. There just wasn't enough time to add one more hat to my day. So eventually what that led to was us transitioning into the full service model. So inside of the full service model, we're still responsible for the installation of the sensors themselves, but the management of the fault limits, the management of the alerts, and then a layer of AI exception handling gets handed over to weights ultimately. So what will happen is AI would be watching the constant stream of data that comes in. When an exception is found based on what the normal baseline for the equipment was, a human analyst would be notified, and then that human analyst would take a look at the FFT and make specific diagnostic recommendations. So based on what he was seeing, he or she, they'd suggest what needed to be done from our side to investigate further, or what could be going wrong. So we had that level of expert analysis attached that we didn't have before, with access to that 24/7. So in order to, there's a fairly large capital outlay that's attached to installing a system like this, especially if you're used to paying sort of a couple $1,000s for a vibration route from a contractor. So in order to justify the expense, I suppose we would look at a Pareto analysis and see where our biggest contributors to downtime were. So we chose assets that would have the effect of 50% or more production loss if one of them went down in the plant. That included high-speed cupping presses, oven exhaust fans, reject duct fans, intricate forming equipment like necking, and vacuum fans, and obviously motors in every aspect. So pretty much all of our large rotating equipment that made sense for us to be looking at routinely, we were looking at routinely. So by means of explanation, I'm going to go through a couple of case studies throughout the 2 years that I was at the company, where we had our major wins and where we had some of our losses. I think it's important to look at both. So in this case, it was a high-speed cupping press. We initially had vibration probes on the drive end and non-drive end of the motor bearings, and we later installed them on the main drive shaft as well. So there was 3 bearings on the main drive shaft and the 2 motor bearings. About a year prior to me arriving at the company, we'd had a failure in this motor, a catastrophic bearing failure on the drive end that had resulted in 8 hours of downtime. Because of the way that this equipment is installed, it requires the use of an external long reach crane in order to get the motor and the drive shaft out. You've got to lift the drive shaft and the motor out in order to get the V-belts changed. So there was a large amount of downtime, and Murphy's Law of Failure says that it's invariably at 2 a.m. on a Sunday when this stuff goes wrong. And that was the case here. There was 8 hours, and that was because everybody managed to do their job perfectly. If everybody hadn't managed to do their job perfectly, that could easily have extended to 12, 16 hours at a conservative cost of $15,000 an hour in lost production. It's probably twice that, but the $15,000 an hour is what I used because it made the numbers seem more palatable to the accountants. So after we had installed the VA on that system, we noticed immediately on the first data capture that a bearing defect had developed. This was roughly a year after changing the motor. It was a mining spec motor, a very, very robust piece of kit, not being asked to do anything that's particularly challenging. So it came as a surprise that we already had a motor defect by that point. As we dug into the data, we found that roughly 1 month after our greasing PM had been done, we saw a creep in the noise floor in the acceleration curve, implying that there was no more lubrication left in the bearings there. What that highlighted for us was that we had a clear discrepancy between what was required for lubrication in that system and what we were giving the equipment. We had already generated a defect at that point, so through that RCA we determined we were going to change the lubrication frequency and the lubrication amount, and we were going to change the motor as well, because we don't want to, we had the opportunity to within sort of 2 months of finding the defect, so we took that opportunity and changed the motor, incurring no additional production loss. But the key takeaway from that is, yeah, we saved, call it $80,000 to $150,000 in downtime, but we also learned something about the kit and how we'd been maintaining it that we wouldn't have been able to learn if we weren't taking really high frequency readings and getting that quality of data all the time. The next were 2 recirculation and vacuum fans. So we had a catastrophic failure on one of the fans in our plant that cost us 10 or so hours of downtime, because it was in a difficult to reach space, which triggered a review of all of the fans in our plant. And one of them was approximately 13 meters in the air, also requiring crane hire in order to fix. An unusual imperial shaft size, so bearings aren't readily available off the shelf, and I'm sure a lot of you have the same concerns where things are half metric and half imperial and half what somebody has slapped together at the last minute to make it work. In this case, that fan was identified as something that was critical to us, and as soon as we'd put the probes on, we had determined that it was in the late stages of bearing failure already. So there was mechanical looseness that had developed, the shaft was damaged, and that was attributed to how the bearings were fitted. So it was a tapered bore bearing, and it hadn't been set up correctly with the initial clearances. The bearings were only 6 months old, and they absolutely shouldn't have been in the state that they were. But now we had identified that there was a problem. What do we go doing about it? Essentially, we looked at the vibration data, and as soon as the RMS acceleration crept above a certain threshold, we'd throw more grease into the bearing, which meant that we were relubricating that bearing twice a week based on the vibration reading that we were getting. But it was enough for us to limit the secondary failures and extend the life of that asset to the point where we could change it inside of one of our routine shutdowns. That was easily 12 hours of downtime saved. I've already spoken about that slide. Thankfully the picture's the same, so you haven't lost out on anything. The next one I want to look at is a gearbox on our necker. So the necker takes the end of the can and essentially reduces the diameter so that you can put an end on it. In this case, This was a belt-driven gearbox, one of two on the Necker, and an enormous amount of tension was put onto the drive end bearing of the gearbox because it was a polyurethane timing belt for the drive. The positioning in the system was critical, so we had to use a positive drive. And the way the system was set up from the OEM meant that the tension in that space was higher than what it should be. This one is a little bit of a sore topic for me because it was a miss for us. We were notified by the system that something was coming. Roughly 7 days before we had catastrophic failure, we got an alert from the weight system saying something's going wrong here, you need to go and have a look. And it flagged the frequency for the input bearing on not the bearing that was being monitored. You can see what the sensor actually looks like, is that little device over there. It wasn't the output bearings frequency that was being monitored, but the input bearing frequency on the other side of the gearbox. So it was sensitive enough, or the fault was large enough that we could read those bearing frequencies all the way on the other side of the box through multiple reductions. I was on leave at that point, and because the team had gotten used to me telling them when things were going wrong, they weren't paying attention to the email alerts, so nothing was done from the 7 days prior to when it actually failed. And it was only after I got back and we did the RCA that we determined, well, look, we were actually told that something was coming here. We had a 7-hour maintenance intervention the day before it failed, and somehow we didn't know to look at it because we weren't paying attention. I think that highlights one of the weaknesses of any condition monitoring program is the human element. You're going to have the same challenges wherever you are, whether it's a condition monitoring team on your site that's telling you that things are going wrong, whether it's an AR model that's telling you that things are going wrong. The people that are responsible for making sure that spanners get put onto equipment need to still go and do the thing. And often it goes into the too hard basket where you're thinking, it's too much mission for me to open that thing up. We don't have a lot of time in the down day. I'm sure it'll last. This one instance was a big learning opportunity for the plant and for the fitters in the area themselves, because it really highlighted that the 8 hours of really, really hard work that they had to do following already 8 hours of hard work during a down day could easily have been avoided if we were paying proper attention. And something like that, where we've had a failure that was highlighted by the system, even retroactively looking back at it, helps evangelize the success of a vibration analysis program. And I use the word evangelizes with deliberate intent, because when your VA system is working correctly, no one hears about it because stuff doesn't break. So it becomes hard to sell its successes. I'll talk a little bit more about that later. So this one, also close to home for me. It was the first major failure that I had experienced in the plant. I'd been in the company for about a month and a half. And picture the scenario. It's the Friday, December the 23rd. One day before you're scheduled to close the plant and turn off production, well, roughly 6 hours before the plant's deciding to go to sleep for the Christmas break. And there's a horrible noise not far from the office. You go out to investigate, and the exhaust fan on the top of the pin oven that's responsible for curing the lacquer in the cans has had catastrophic bearing failure, and that catastrophic bearing failure has resulted in the impeller tearing itself apart and the shaft self-destructing at the same time. Also caused damage to the volute of the fan, which thankfully wasn't too severe. So now on December the 23rd at 3 o'clock in the afternoon on a Friday, who do you go to for repair? The simple answer is no one. There was no one available that could accept that broken part and fix it. There was no chance we were getting a spare because we didn't have a spare fan assembly, we didn't have a spare rotor. We really had to bite the bullet, and it was an 8-day repair. Thankfully, and it's a double-edged sword, I suppose, because people might have been available if it had been not over the Christmas holiday, but we only endured a 6-hour loss of production for this because we were scheduled to turn off that night. But had we not been, this easily would have been 24 to 48 hours, depending on when it had happened, at a cost of $400,000, $500,000 on a single failure. During the RCA following that event, it was determined that these bearings actually failed twice a year. Not to the degree that they failed here, but the bearings themselves developed excessive play within approximately 3 or 4 months of being installed. Now, I don't know why that was tolerable in the past, but as it turned out, we threw some VA probes onto it, and we determined that the bearings were cooking their lubrication out of them within a couple days of being in operation. And they were quite frequently lubricated, once a month, but obviously once a month is not enough when you're dropping your grease once in a week. So as a result of that, we changed the lubrication practices. We put high temperature resistant grease in there because the ambient temperature was roughly 120 degrees. And we put the vibration monitoring probes on there as well that indicated primarily that we had imbalance, because you can see the quality of the repair of the impeller that we had to put back in was challenging. We couldn't get anybody to balance it because it was Christmas holiday time. So we put it in and we dealt with sort of 6 to 8 millimeters of RMS velocity. And we ran with that impeller in for as long as it took for the spare to come. So that was, I think, 12 weeks from that January is how long it took for the spare fan assembly to arrive. And we haven't had a failure there for the 2 years since we've installed the VA and changed the greasing schedules there. So if we were looking at, if it was just bearing changes, 4 hours twice a year, to the maximum possibility of 48 hours twice a year, that one failure that we've prevented on this single piece of equipment has paid for the implementation of the VA system many times over. So that's just a little bit more about the situation where that was installed. You can see there was space for the grease to go in. The sensors lived inside that little box, which unfortunately got up to 120 degrees, like I said, and melted the sensors, probably within 3 months of us installing them, which is fair to them because they did say we shouldn't use it in temperatures of higher than 80 degrees, but I was a little bit desperate. So we replaced one set of those sensors after that first period, and then those also cooked themselves to death, but it was worth the cost because of what we were trying to nurse. Eventually we went onto a tethered system that was not coated in plastic and much more tolerant of the temperature in that environment, and while still operating outside of their temperature zone of happiness, those have been working pretty much flawlessly since then. So, as detailed already, the cost of that failure was roughly $60,000 if I'm going on the really conservative side of downtime cost. The reality is that could have been so much more. Things just went really, really well for us in that environment. We managed to get last minute work done by a contractor contacted through a Facebook marketplace advert rather than through anything else. I mean, sometimes you've got to dig real deep to get work done. So credit to the team that we managed to do it, but it could have been much worse. And I don't think that this company is unique in that challenge. I think that things go wrong for everybody when they're not supposed to. Having the VA probes goes a long way to correcting that. Now, Waits might not enjoy that I share this, but I have a somewhat off-label use for their product as well. So because it's expensive to implement, and because we had roughly 350 assets that needed to be protected, we had to become a little bit agile or MacGyver-ish in how we applied that. So because one sensor doesn't necessarily have to be permanently attached to a machine, what we were able to do was take that accelerometer, reprogram it to multiple different assets and take ad hoc readings, and for whatever period we wanted that sensor to live there, we could then capture data every 15 minutes, an RMS reading, and every day an FFT. And that produced enough data, at least in this case on our compressor. It was a 350 kilowatt compressor on that site, where we diagnosed that there was a bearing issue in the motor and multiple bearing issues in the gearbox, enough that we could nurse it over the sort of month that we were monitoring it, to the point where we could change those components. But having the agility to take a sensor and move it from place to place, it essentially becomes a data collector for a tiny fraction of the price of a data collector, because all of the intelligence lives in the cloud. All right, so what the get was for the company that I was at was essentially $500,000 on the conservative side of avoided costs. So that would have been downtime, it would have been reputation damage, it might have been requiring a competitor to fill orders, because sometimes we were only 4 hours ahead of our customers in terms of the production that we were running, and you can imagine the pressure there is immense. It was avoiding the human's interaction with that space. A lot of these assets, in fact, all of them except for the compressor, were in areas that were incredibly challenging to get to. They required lifts with cranes on site, so mobile equipment handling, suspended loads, long hours at the job, all of that avoided. And then personally, peace of mind for myself. I know when I have bad actors in the plant, I struggle to sleep I have had nightmares about things that I've been maintaining my entire professional career. And knowing that you've got a system that's sitting in the background, quietly listening to how things are vibrating and letting you know when they're going wrong, actually is tremendously helpful for your personal peace of mind. So if you're looking to do something similar in your implementations in your plants, how you get there really is by being incredibly vocal about the cost of downtime. So doing your RCAs religiously, making sure that you're incredibly precise in your RCAs as to what the cost of that downtime was. And it goes so far beyond the cost of the actual production loss or the cost of the failed parts, because all of the human interaction with the machines, like I know people say that safety has no cost associated to it, that's too great, but the reality is people get hurt when they're doing non-routine tasks, and all of these would be non-routine tasks. So make sure that throughout your RCA process you highlight the cost of that failure very, very clearly and indicate whether having some forewarning would have prevented that cost from occurring. And once you've got that information, if you've got 6 to 12 months worth of information, and if you're in a production constrained environment like I was and am, then that justification, the CapEx justification, becomes trivial. The ROI on even a large scale implementation of this is a matter of months rather than years. And I don't know an accounting department that would turn down an ROI project with a 3-month return on investment. I know I'm struggling to get things across the line when they're knocking over 3 years, but if you're less than a year, it's almost automatically a yes. And you can only do that if you have all of the information that supports your claims. And you do that through the RCA process, through meticulous logging of those costs, and then presenting them in a way that makes it very hard to ignore. All right, we are in the questions phase now. I'm actually 2 minutes over.
We've got 3 minutes left. Anybody questions? Yeah.
Is that vibration sensor only, or you get integrated the temperature control, temperature measurement as well?
Temperature measurement integrated into the sensor.
Okay, so and one more thing. So you have to use 2 sensors for the one motor, or you can put 1 sensor for the motor?
That depends on I suppose, your level of due diligence. I have seen drive-in bearings and non-drive-in bearings fail despite how the drive-in bearing would be higher loaded. You can get by with just having 1 sensor on the heaviest loaded side.
All right, thank you.
Was the AI tool that you were using for insights a AI tool that Waits supplied, or was it something to do with the platform and the IT infrastructure that you had in the company you're working for?
It was a part of Waits' system specifically, so we didn't actually see much of the AI information. The AI information was used to highlight exceptions to the human analysts on the Waits team.
And it came from a Waits specialist or something?
Yes. So the interaction that we had with the vibration analyst was always with a human being, and it was specifically targeted to what was going wrong with my components.
Any more questions? I think we're about on time.
Yeah,
thank you. I know, Luke, you'll be downstairs. Anyone wants to grab you and ask you any more questions?
Yeah.
Perfect. What I'd like to do before we leave, one, take your phone out, fill in the evaluation form, please. We just really want to give feedback to all of the speakers that you're seeing today. Second one, exchange sessions tomorrow. They are birds of a feather groups where if you go along to them, you will have an hour to discuss a particular topic. Could be anything, there's 19 of them. Put your name downstairs if you possibly can. We're starting to run out of certain sessions, so if you want anything or you want to attend anyone in particular, now is the time to put your name in. And finally, yeah, brilliant. Thank you so much, Luke. Want to give him a round of applause. Thanks, folks. See you soon. We'll start again in about 5 minutes.